Well, hey there, fellow narrow gaugers and steel industry historians. So today I want to talk a little bit about the Tod engine here and what it is and what it did. I've been getting a lot of questions lately now that we've been working on this thing again as to what the Tod engine is. So let's go over it. So basically, it is a stationary steam engine. It is what they call a cross compound type. Meaning that you have a high pressure cylinder over here and a low pressure cylinder that are across from each other. That's where you get cross compound from. It has a 20-foot flywheel back there, and about 75 RPM would produce roughly 4,000 horsepower. And it was used to power a rolling mill at the Youngstown Sheet and Tube Brier Hill Works, which is was about 5 miles due west of us. And it was built in 1913, installed, first operated February 1914, and ran up until 1979. So about 65 years that this engine was in service. We acquired it in 1995, and from September of, I think starting September of 96 through, probably through the summer of 97, we were given access to the plant to go in there and dismantle it and move it out. And all we had to do really was take it out of the building it was in and then move it to the other end of the plant into this big empty building, the old plate mill building, where it was stored there for 9 years until we purchased this property here and moved the engine here to our location. So this whole project actually got started. Everything here got started because of this engine. The reason that we own the land and everything else. So this is basically the heart of the entire Youngstown Steel Heritage J&L Narrow Gauge Railroad operation was the preservation of this engine. Our ultimate goal is to have this engine to operate again and to operate it on steam using 2 of our J&L porters that provide the steam to run it. I hope 2 boilers, 2 locomotives will be sufficient to do it. I think so. And this will be no load. We're just basically trying to get the flywheel to spin again. So let's go over how this thing is built. So the steam coming in from the boiler house would come in through this valve. This is a 12-inch throttle valve into the high pressure cylinder. Now, if you note, there's 2 sets of valves here. So this is piston valve, but it's dual piston valve. So you have a piston valve for the steam and another one for the exhaust. The reason for doing that, especially in stationary applications, is that the steam comes in at whatever the temperature is, 300 degrees thereabouts, at 150 psi, expands, pushing the piston, and then when it exhausts at a much lower pressure, it comes out at a lower temperature. Because with steam, temperature and pressure are related. So if it's a lower pressure, it's also a lower temperature. Well, it comes out at that lower temperature, and if you had one valve doing both, like on our locomotives, well, that hot steam would go in, and then that cooler steam would come out, and it would serve to cool down the valve and then the valve chest a little bit. It doesn't cool it down much because there's not much contact time, but it's enough that you could lose 3, 4, 5% efficiency. Well, on a steam locomotive, that doesn't really matter too much, but on a stationary engine where you're trying to get the maximum amount of this thing day in, day out, and you're in kind of a controlled environment here, wringing every bit of efficiency out of the engine is incredibly important. So you build it with 2 valves. The steam valve stays hot. The exhaust valve stays at that lower temperature, and then you gain that little bit of efficiency. So the steam coming out of this cylinder would then go down and then under the floor and then up into this one. And many of you recognize it. It's a coreless cylinder. This one is 68 inch in diameter, and the steam would come into this cylinder at a much lower pressure, let's say 15 psi maybe, pushing against a much larger surface area of this piston, and then exhausting out into a condenser. So it's exhausting out into a negative pressure environment. So you're getting 15, let's say, psi in, it's coming out at -5 psi, so that's about 20% or 20 psi of effective pressure that can push against the piston. And since that pressure is so much lower, you needed a larger diameter. That's why this is so much bigger. One interesting thing about this is that a lot of stationary steam engines, most of them were not built with two different types of valve gear. This is kind of unique, and especially amongst rolling mill engines, there weren't very many that were made with two different types of valve gear. This was a idea and a design of a fellow by the name of Julian Kennedy, who was a fairly famous steel mill designer and builder in the early part of the 20th century. And it was designed to give the maximum amount of efficiency with the coreless cylinder, and also to give the much better speed control that's available with a piston valve. So they teamed them both together, and they came up with this engine. Now, in the plant, originally, there were two of these built, and two of them operated, and they were side by side. Let me take this down here. Okay. So here we're looking at, let me get this thing straight. Okay. So here we're looking at, this was the blooming mill building at Brier Hill. So at this end, you had the blooming mill, so the ingot would come in here, go back and forth a bunch of times, be squeezed down into a billet or a slab, and that engine looked like that. And it was a twin tandem compound reversing engine, also built by William Tod. So your slab would then come out, and then there was another mill right here called a 24-inch continuous mill, and there were 6 stands in a row. And then that slab would make one pass through there. And then that one was driven by a drive shaft that came out of the motor bay and came out of this engine, which is the sister to the one we have here. And then, of course, here is our engine. So they're side by side originally. So that steel would come out, and then it could transfer over, then go over to the warehouse bay, or it come over here, transfer down, and then go through 1, 2, 3, 4 stands, transfer over, go through the 5th stand, and then the 6th stand, and then out to the gang shears, which then would cut the resultant bar into several lengths, then out to the cooling beds, cool down, and then loaded in the rail cars down here. So that's basically what this mill was set up to do, was to take ingots and to turn them into something called sheet bar. And sheet bar was, anywhere from 3/8 to 5/8 inch thickness, 6, 8, 10 inches wide. And it was the raw material for the hand sheet mills that was then, very prevalent for producing sheet metal. And that was a technology before 1926, when the first continuous hot strip mill was invented. And then shortly thereafter, the hand sheet mills all went out of favor, and then during the Depression, most of them were all scrapped, and hot strip mills were put in their place. So this mill ran up until, the early 30s. Of course, the Depression starts. The need for flat rolled products goes way down. They shut the entire Brier Hill works down. They keep the Camel works across town running, but they shut all of Brier Hill down for several years. Well, in the meantime, Youngstown Sheet and Tube trying to figure out, well, what are we going to do once we get out of this depression, because they knew that we would recover. What can we do? How can we position ourselves as a company to be able to capitalize upon business opportunities after the Depression? Well, the one was, let's build a hot strip mill. So they put in the 79-inch hot strip mill at the Camel Works. And another thing was the installation of the seamless tube mills at Camel, because they also felt that going forward that there would be a big demand for seamless pipe, especially for the oil drilling down in Texas and Oklahoma. So they put in a seamless tube mill for that. So the blooming mill and the open hearth and all that Camel Works was re-geared for the making of slabs to feed the hot strip mill. But to make the rounds, which are solid round shapes for the seamless tube mill, they didn't really have the capacity there. So they decided, so the ownership of Youngstown Sheet and Tube decided to put in the seamless tube mill, and the seamless tube mill would take round shapes that were anywhere from 4 to 6 to 8 inch in diameter and run them through the seamless tube mill and creating seamless pipe. So they needed a way to make those tube rounds. Well, they had the Brier Hill Works, which had been shut down for several years during the Depression, and they figured out, well, let's convert Brier Hill from making sheet bar, which they no longer needed, to making the tube rounds, which they didn't need. So they did some modifications to the blooming mill. They eliminated the continuous mill, took this out completely, took this engine out, put in a 35-inch intermediate blooming mill over in this area with a drive shaft that came over here, and then there's electric motors over here, and then converted the 24-inch merchant mill into a round mill. So then, when they started the plant back up, the ingots would come in, be squeezed down into bloom shapes, go through the intermediate blooming mill, be converted into the large diameter rounds that they needed for the large pipe. And if they were making smaller pipe, those rounds would then get squeezed down through the round mill into the smaller 4 3/4 inch and various size tube rounds that would then be made into the smaller seamless. So from, let's say, I think it was like 1936 or so, when Brier Hill reopened, it made mostly tube rounds from then up until 1979, when the plant was shut down for the last time. So, okay, so how does the Tod engine drive the rolling mill? And you can see this drive shaft here, and there's a gearbox. 1, 2, 3, 4, 5 gearboxes, and actually 6 power shafts that ran into the mill stands. And there were couplings on either end of the crankshaft of the engine to turn all of this. So when this engine turned over and that flywheel spun, it was also turning about a few hundred tons of 12-inch diameter shafting and turning all these gears. So it was quite a bit of machinery all moving off of this engine. So we take you around and show you that coupling. Now, those of you familiar with the steel industry can recognize this as one half of your universal mill coupling. And then there was a forked shaft that would fit in here on either side of this bearing block. And then there would be another one of these a few feet away, and between those two and that central piece, that's your universal joint. And this was that was a universal drive that's still being used in the steel industry today. So over here we have our 20-foot flywheel, and this other smaller wheel here, which is 6 foot in diameter, is the governor wheel. And how this engine ran, it ran off of a centrifugal governor. And this here, you can see this, and on the other side there's another one. These are the flyweights. So as the engine would speed up, those would move outward, and as they moved outward, it would reduce the amount of throw of the eccentric. This is an eccentric right here, called a swinging eccentric. So the faster it goes, the less that eccentric would move, and that eccentric opened and closed the steam valves. So the faster you're going, the less this moves, the less steam is being admitted into the cylinder for each stroke. So to change the speed of the engine, you would either add or remove weights here to get your governor setting. Now there was also another thing on this, which was a wooden block and a spring that pushed against a part of the governor and acted as a snubber. So it would, basically it would reduce the amount of oscillation of the governor. So unlike a steam locomotive where you pull out the throttle and the amount of steam that's going through the throttle controls your speed, this here is all done automatically through this governor. Once you get up to that speed, this thing takes over, and then you can just open up the throttle all the way, and the speed will be handled by the governor. Question is, will we ever have enough speed for this governor to do anything? Don't know. All right, so now as you can see, the engine is sitting up on a bunch of steel. Now normally there would be concrete right up to the bottom here, and then an inch or two of grout to grout it in, and this concrete foundation would be several feet deep. Unfortunately, we don't have a lot of money, and we had even less money back when I moved the engine, so all I could do then was just pour a concrete slab, put a flywheel pit in it, and set the engine up on blocks with the expectation that someday maybe we'd have enough money for concrete. We could at least fill this in and put somewhat of a foundation under it. Well, that's what we're going to be doing now, is putting all this concrete in. So with this engine not being under any load, with it running at somewhat slower speeds, I think we'll have enough mass of concrete, even though it's a rather thin foundation, to handle the occasional operation of this engine. So that's one of the things I'm going to be working on over the winter. Another thing working on is putting the flywheel bolts in. When we brought this engine in and set it up, we had the cranes in there and put the flywheel down in the pit, and then put the crankshaft up on top, and then set the top piece on there. I put just enough bolts in there to hold everything in place, but thinking, eventually I'll get around to putting the rest in. Well, other things happened. We built the building, put the crane in, did a cosmetic restoration on this, then we started with the narrow gauge railroad project, and it just wasn't any time, really need to put the bolts in, so they never got put in. Well, we're putting them in right now. And so thanks to a Harbor Freight porta power and this little jig that I made up out of 2x4s that holds the porta power in position, now I can get up there and clean the hole out, and then get the bolt ready and get the bolt started in place, and then push it the rest of the way in with the porta power, because it's not a press fit, but it's not a loose fit either. It's kind of a, then you get a little bit of interference, but not too bad. The 10-ton porta power has no problem pushing them in. So the goal is to get all of those in, to get the nuts on the back side. And then the other thing that has to be done is to install the shrink links up here, which are these dog bone looking pieces that fit in there. And what you do is you heat them up, and they expand just a little bit when you heat them up, but it's enough to put them in there, and then when they cool, they crunch down and they hold the flywheel together. So it's 4 of those, and I have them, and we're going to put those in. Almost didn't have them. Someone stole them off of us at one point. I had to go down to the scrapyard and buy them back from the scrapyard, but that's, living in Youngstown. I learned, protect the stuff that you want to keep. All right, so this is the high pressure side bed plate, 84,000 pound casting. You barely see it behind the ammo box, the piston rod. So the crosshead and the connecting rods are outside, and they'll be brought in due course. as needed to put back on. Don't mind a lot of the mess in here. I've got everything out from under the engine as I'm going through and figuring out what stuff we need to keep, what stuff can go elsewhere, because over the years, that's a real handy place to put stuff. Well, now we're going to fill it full of concrete, so there isn't going to be room for the overflow storage anymore. So it all has to go away. All right, let's take a little gander up here. All right. So here we are on the high pressure side. There's your governor wheel. Here is the steam eccentric, and then there is the exhaust eccentric. And you can see those are rockers here, and then 2 reach rods, and then here's our throttle valve. And the same thing on this side, but we have the cordless side. I don't have the rocker in yet, and of course don't have the reach rods in, and don't even have the eccentrics in for the exhaust side yet. Now we'll go up on top of the cylinder here. So you may be unfamiliar with what this thing is. We have one on either side. So these are tail rod supports. So the purpose of this is to take the weight of the piston off of the cylinder. So like on a steam locomotive, you have the weight of that piston and the end of the rod that rests on the bottom of the cylinder as it's going in and out. And over time, you'll wear away at the bottom of the piston, you'll wear away at the bottom of the cylinder, and from time to time, you have to go and rebore cylinders and make new pistons and all that. Our porters are like that. When you look at it, there's a gap between the top of the piston and the top of the cylinder. There's a little bit of a gap right there, and that denotes that things have worn away going back and forth. Even with cylinder oil and all that, it still wears. Well, on an engine like this piston is 68 inches in diameter and fairly thick. Well, that would just wear away at that cylinder with like nothing, unless you had some way of supporting it. So what they did is that they had the piston rod that would extend through the piston and then out the other side of the cylinder, and then there would be a support out there and a slide like another crosshead, and between this tail rod and the crosshead itself, the piston would not weigh down or bear on the cylinder. The only thing you'd have is the spring tension of the rings pushing against the bore. So that gives a lot longer life to the cylinders and to the pistons. Now, some early steam locomotives had that. Like some early Pennsy K4s had them. Railroads decided that it just wasn't advantageous to adopt that design, and they got rid of them, figuring it was probably not worth the trouble, and then they would just rebore and re-sleeve cylinders and make new pistons as needed, that it wasn't worth all that extra effort to keep those tail rods steam tight and all that. But in a stationary application, again, because it's in a kind of its own environment here, and they're looking for maximum efficiency and also maximum uptime on this engine. That was the other thing, which is, unlike a steam locomotive, you could take one steam locomotive, send it to the shop, and another one takes its place. If this engine isn't running, that mill isn't running. So this thing had to be set up so that it would operate as much as possible. So you didn't want to have something on here that was going to break to take the mill out of service, because you're losing thousands of dollars a minute whenever that mill's not running. And then you want your upgrades and your maintenance to happen during planned maintenance outages. So in between those outages, you want this thing to be running constantly. So this design of this is just, everything is gigantic. The bearings are huge. The size of all the parts are oversized. You have the tail rods. You have all this on there that says, we designed this thing to run as long as possible, putting out its rated horsepower and to not have any issues. And that largely was true, because over the years, and then going through this engine as we tore apart, we could find the original numbers on a lot of the parts. Most of the parts on this thing are original. They all have the contract number, 13798, which was the William Tod company number for this engine. There are some parts that actually have the number 13799, which was that continuous mill engine. So interestingly enough, this high pressure cylinder casting is 13799. That's off the continuous mill engine. And also, the number on the hub of the crankshaft is 13799. So it's telling me that at some point the original crankshaft for this engine was removed and then replaced, and then this one was put in its place. A lot of these engines had spare crankshafts, and so in 35, when the other engine was taken out, they saved the crankshaft and put it in reserve. And then at some point, they refurbished it and swapped them out with this one here. So it's interesting that of the two engines, a little bit of that other engine survives in parts on this one. So, all right, this video's gone on long enough. Kind of explained everything to how this thing worked originally. As you can see, we still got a lot of work to do on it. Fortunately, it's all inside, present and accounted for here in the building. So it's just a matter of doing the work on it. And now that winter's coming, we're going to put the locomotives away for the winter and concentrate some effort on the Tod engine. And then come next spring, we'll get back to working on the steam locomotives again. Yeah, it seems like we're jumping around a little bit, but for my personal interest, every once in a while, I need a change of pace. I need to do something a little bit different. And, we've been working quite heavily on those steam locomotives all year, and last year, and the year before, and, for the last several years. Like, you know what? We need a little change of pace. I want to do something a little different for a while. Let's spend some time on the Tod here and get it a little bit further along. Because I'm not getting any younger, and if I don't get this thing together before I die, I don't think anybody else will take over from where I'm at. So it's imperative that we actually get some of these projects done. All right, everybody. I will be creating more videos about this project as we go forward. But for now, everyone take care.